So yesterday, what you did is that you figured out the spring constant. So, let's see. So you took like a half a kilogram mass, you hooked that up, okay? We measured how far it stretched, and I sent you all that data. So like that half a kilogram mass, I think stretches like 6.5 centimeters. And then we swap that out for a 1 kilogram mass, and that 1 kilogram mass stretched it 13 centimeters, which makes it nice because that exactly follows Hooke's law. So you should have a graph. If you need graph paper, I can give you also graph paper, where you have force here and you have elongation here, and it should be this nice linear function. Okay? So the quick refresher on this whole concept is that this is a force and distance, so this is a measure of work. And so the area underneath this graph is what is your value of work. That's in Newton meters, that gives you joules. So the farther that you stretch this spring, the more force it takes, okay? So it isn't like, oh, it's the same amount of force all the time. No, to stretch it further and further and further, you need more and more and more force. So you should get a slope of that line usually around 75 newtons per meter, okay? So that's going to be this value of K. So you're going to draw the line, draw the slope of best fit, find that value. So then they said, okay, well, that's cool, we got that part. Then the next part is that they took a 1.5 kilogram mass and which is easier said than done. And they hooked that up. Gravity storm. Nothing like trying to do this one. Somebody come up here and help me. Aiden, come here. Hold that.
I'll take the blame for that one.
No, that was on me. That was on me. Hold that again. Mm-hmm. Now, hold that. Top. There we go. Now we got it. Okay, we're cooking with gas now. Okay, so after much trial and tribulation, we finally got this deal set up. And so what they did is they made this thing oscillate back and forth like this. So here's what I want you to visualize in terms of like the position time graph. So imagine that we could take a pencil, right? And we're going to attach that to the weight. Okay, so imagine we have a pencil like this. And then we're going to drag a piece of paper past it as this thing is oscillating. So as this thing is oscillating, imagine this pencil is going back and forth like this, okay? And at the same time, we're dragging a piece of paper along that side. So what happens is that you're going to generate a graph on a position time graph that's going to start like this, and it's going to go like this. So imagine that you're going to start with this pencil at the top, and then it's going to oscillate back and forth like this, okay? And as it does, you're going to drag that piece of paper along there, okay? Cool with this. Now, this can also play out with circular motion. So imagine like you have like a microwave, right? And you have a cup on that microwave. And the only thing you can see, imagine this is round and it's a microwave plate. And imagine that you could see this cup sitting right here. So as that microwave spun around like this, okay, what you would see is that you would see that cup going back and forth like this, okay? You would see it in simple harmonic motion. So you would see that motion going back and forth. Here would be like the middle, then you would have an amplitude over here, and then you would have an amplitude over there. So imagine that's there, and you're going to see this thing spinning. So that's going to be also how this relates to simple harmonic motion. So simple harmonic motion can be using to describe something that's going up and down, or you could have something that's going around in a circle. And that could apply even to the Earth as the Earth goes around in its orbit, or the moon, or whatever that is. So, anybody remember what omega is? What is that a measure of?
Angular velocity.
Angular velocity in
Radians per second.
radians per second. So this is radians per second. Okay? Now, this should make sense that omega also equals 2 pi f. So here's another equivalent statement, and we're going to use this later on in the lab. So 2 pi f, if you look at the units, well, that's 2 pi radians. Frequency is radians per second, okay, or in events per unit of time. So both of these have the same units of radians per second. So this is why when you look at something spinning like on a microwave, where it's going around in a circle, so many radians per second, that's why this is equivalent to 2 pi f. So we're going to use that in some of the equations later on today, but I just want to plant that seed. So what you should have is, you should have a position time graph that goes like this. Your velocity time graph, hold on, grab mine. Is, let me clear all this off. Let me get this out of the way. I can do this without completely dropping it. Score. And your velocity time graph is going to look like this. And your acceleration time graph is going to look like this. Okay? So, your position time graph is going to start up here at the top, and then it's going to fall. Your velocity time graph is going to start at 0, then it's going to come down here like this. Your acceleration time graph starts with a negative acceleration, because initially that thing is going to fall, so you're going to have negative velocity, which is increasing. So that's why you're going to start with negative acceleration. Now, these points where you have relative maximums or minimum, or where it crosses through 0, are vital things to look at. So if you look at this acceleration time graph, when this crosses 0, here's a common misconception. Everyone goes, oh, it has no acceleration, that means that it's at rest. Okay? If something doesn't have an acceleration, that doesn't mean it's at rest. I mean, I can walk along at a constant velocity, okay? I'm not accelerating, but I'm still moving. So you can have no acceleration, and you can still have motion. So the only thing that's going to happen when your acceleration goes to 0 is because that's what's taking place when when the forces are imbalanced out. So as this thing is oscillating back and forth, at this point where you have no acceleration, that just means that the downward pull of gravity is equal to the upward force of the spring. That's all it means. Okay? So when you so initially, and visualize this as this thing is falling, you're up at the top. So the downward pull of gravity is greater than the upward force of the spring. So as it falls, your upward force of the spring is getting bigger. Because remember, F equals kx. So when you have negative acceleration, that means you have a negative net force. The only way you can have a negative net force is if the force from the spring is greater than the force due to gravity, because we're defining down as being a negative value. I'm sorry, I screwed that up. I wrote that wrong. Hold on. That the force from the gravity is greater than the force from the spring. Okay? That's why that's pulling it down. At this point, these two forces become equal. Once you cross that threshold, then you have positive acceleration, because then the force from the spring, because it's gotten stretched, is now bigger than the force of gravity. Oh, now I have positive acceleration. So if you look at what happens on your velocity time graph, remember, if acceleration and velocity have the same sign, it speeds up. So at this point up to here, I have negative acceleration. My acceleration is going to go to 0. That's at this point, okay, then I'm going to have positive acceleration. So that's going to make that negative velocity slow down. If I were to draw the tangent line here, okay, my tangent line on my velocity time graph gives me my acceleration. So this has no slope, so this is an acceleration of 0. That's when this velocity, or this is when this acceleration time graph crosses 0. So you have to see how all three of these graphs correlate, okay? Just don't look at them in isolation. You have to look at them individually. Now, here's the deal. So let's say that I want to find the mass of, let's say that that was kind of cool. So let's say that you have a spring like this, and you want to figure out the weight of this mass, okay? So we're going to try and figure out what's called the gravitational weight. So if you go to your graph, okay? If you go to your graph where this whole thing started, and you know how far this mass stretches that spring. So if you know it stretches at a certain distance, you can come over here and you can figure out how much force is going to correspond to that. The farther it stretches, the more it weighs. Now, that works well on Earth or on the Moon or Saturn or something like that, where you have a gravitational field. So that mass is basically trying to fall down a gravitational well, and it's taking the spring with it. That works phenomenally well if you are in a gravitational field. The problem is that if you're like in the space station, the International Space Station, or if you're in deep, deep space, and I take that half a kilogram mass that doesn't have, and I'm not in a gravitational field, and I hook it up, well, it's just going to stay there. So if I don't have a gravitational field to stretch the spring, I can't find the weight of it because it's not getting stretched. So what we're going to try and find is what's known as the inertial mass. Now, inertial mass is based upon how easily it is to get something to speed up, oddly enough, based upon its inertia. So remember, what's the only thing that determines inertia? It's the only one thing that determines inertia. The amount of mass in the object. That is it. Nothing else. So if I take this half kilogram mass, and if I'm on Earth, I can kind of move it around, and I can get a feel for how much force it takes to make it speed up and slow down. But if I take Hank, right? So if I take Hank and do that same thing, right? Hank has a lot more stuff in it. So it's a lot harder to get Hank to move back and forth because it isn't a function of the gravitational field. It's the fact that Hank has a lot of mass. And it's hard to get that to move. But once you get it moving, guess what? It's hard to get it to stop. So, Kelsey, I need you to adjust that camera. So, we're going to go right here. So you might have to like tilt that down.
You need me to come back a little bit?
No, we're okay.
Okay.
Okay? So, and for those of you that are zooming, okay? So, I'm going to take this and I'm going to clamp it down to the tabletop, like so. Like so. Okay. Zoomers, can you see this? Somebody talk to me. Can you see this? Huh?
Yeah, we can.
Okay. All right. Oh, man. Oh, I just hit my funny bone. Oh, that sucked. Oh, workman's comp. Oh, I don't know if I can teach the rest of the day. Okay. So, COVID. Oh, okay. All right. So if I take this, right, and I give this a pull, right, that thing's going to oscillate back and forth. Now, I can figure out the frequency of this, right? I can sit here and go, okay, that's going to vibrate with a certain number of events per unit of time. Now, that's actually pretty fast, so that's going to have a relatively high frequency at a long period of time. Now, what I'm going to do is, I'm going to take that, and then I'm going to do the same thing, but then I'm going to put this mass in here like this, okay? So now I've increased the mass, right? So here's what I want to look at. When I do this with this mass in here, three things could happen. It's going to vibrate less often, okay? Period's going to go up. It won't have, or it's just going to be the same because it's the exact same spring. Or it's going to vibrate faster, okay? So it can go slower, it can go the same speed, or it can go faster. So, we'll ask the newbies, who are kind of wearing the red sweaters. That's kind of cool. So, what do you think? Faster, slower, or the exact same?
Slower,
Why?
because it has more mass. So if you apply the same force, they'll have a smaller acceleration.
Okay, so what's creating the force?
You're pulling on it,
That's true, but then what's going to make it go back?
the spring and the like metal bars.
Yeah, so these are basically like horizontal springs, okay? So, now, why does it always stop in this position? Why doesn't it stop over here or stop over there?
Because then it has elongation and it's not at the lowest energy state.
There you go, okay? If I pull this over here and let go of it, if this was at the bottom of the energy well, it would stay here. If I pushed it over there, and that's where it was most stable, that's where it would stay. So this thing is always going to settle at the lowest energy well, right? So now, if I pull this over, now, so visualize, compare that to what happened this. So when I put that mass in, what happened?
Slows down.
It slows down because you have a lot more mass to make move. So even if I do this even more and put more mass in there, okay, now when I do that, okay, it's kind of hypnotic. So here's what I want to know. As mass increases, okay, I want you to think this through. As mass increases, what happens to the frequency? Is there a direct or indirect relationship between mass and frequency? Party girl.
Indirect,
Why?
because as mass increases, frequency decreases.
It's true. So as the mass in this system becomes bigger, frequency becomes less. But what's the relationship between period and mass? Remember, period is a time for one oscillation. That's a direct relationship. So there's a direct relationship between mass and period, but there's an inverse relationship between mass and frequency. Okay? So that's why you have to keep track of what you're talking about. So, could I use this system if I knew the mathematical relationship? It does this on Earth. Okay? If I took this to the moon, do you think it would behave in a similar type fashion? Yeah, okay? Because of the fact that what's making, notice, yeah, gravity is pulling it down, but at the end of the day, what's happening is that these two oscillators, the two on the side, okay, they want to return back to an equilibrium position. which is independent of a gravitational field. So if I knew like a curve, so if I knew, oh, a certain mass causes a certain frequency of oscillation. So if I knew that value, and if I knew what that relationship was, and if I could measure the frequency, I could go back and I could figure out what the mass is. So I couldn't use a Newton scale to hold it up because the Newton scale wouldn't measure anything. So this would be an example of where you measure an inertial mass because it isn't dependent upon a gravitational field. So if I knew what that period of oscillation was, I could work backwards and I can figure out how much mass that I put here. Okay? Got the idea. So this measures inertial mass, which is independent of a gravitational field. A Newton scale or a spring measures the gravitational weight because that has to interact with being pulled down by a gravitational field. Okay? Now, you can also have a situation where you have springs that operate horizontally. Okay? You all are used to springs going vertically. Oh, and the gravitational field is pulling it down. But you can also have springs that oscillate horizontally. So if you all remember back when you did the CART lab, and you had the plunger on the end of it, and that plunger got compressed and it stored potential energy and it pushed the cart back, okay? That would be an example of a situation where it's not dependent upon the gravitational field. So if you can make springs oscillate horizontally, then you don't have to worry about a gravitational field because all you're doing is storing potential energy and kinetic energy of the spring. There is no UG. It's only us and the kinetic energy. Got that visual? Okay, so let's get that. That down, so that's out of the way. Now, so open up. Okay, so we're going to kind of work through the second part of the lab together so it's going to be kind of like a group thing, okay? So let me turn out the lights so maybe y'all can see it out at home a little bit better. Okay, so these are all questions referring back to what you all have already done, okay? So let's start with this. So what's the net force acting on the system at 1/4 T? So think about this. What is net force equal? What can you multiply together to get your net force? Dear Lord, please someone answer this question.
Mass and
Last time's acceleration. God bless you, Kelsey Thurman, because bad things would have happened if no one would have like, I don't know. What could I multiply together to get net force? Not sure, Rocky. Okay, look, mass times acceleration, right? So go to a 4th T, right? Go to your acceleration time graph and figure out what the acceleration is at 1/4 T. Dina, what's my acceleration at 1/4 T? 0. So I have no acceleration at 1/4 T, so what's the value of my net force? 0. Okay? I'm not saying there aren't forces acting on the system. I'm just saying that the net force is equal to 0. Okay. Now, here's a new equation. And let me explain what this is going to give you. So, yesterday, if you look at what calculations that you did yesterday, like on question number 9, you found the position as a function of time. So yesterday, you used, oh, hold on. Yesterday, you all used x equals a cosine 2 pi t over t. So yesterday, and this is what's on your equation sheet, by the way. So yesterday, you all used this to find position as a function of time. Dependent upon your amplitude, this is how much time it elapsed, this is the period of the oscillation. So this is a similar type thing, okay? But this is going to be V max sine 2 pi t. Now, here's the deal. You've got to figure out, and this is what you already know from this previous page, on question number 10, you all used V max equals 2 pi f a, right? Now, here's the other thing that sometimes you'll see this written, and this is what I talked about earlier. 2 pi f is the same thing as omega. So sometimes you're going to see this written as V max equaling omega times your amplitude. Now, if you look at the units, this is radians per second. This is your amplitude, which is B in meters. So you get meters per second, which is V max. And again, think this through. As omega gets bigger, as that microwave dish spins faster and faster and faster, you're going to get a bigger and bigger velocity. You're going to get a bigger and bigger V max. So the same thing's going to happen here. If this thing gets a bigger and bigger frequency, as this thing vibrates faster and faster and faster with the same amplitude, guess what? You're going to get a bigger and bigger and bigger V max. So you have to look at what's playing into this equation. So you should already have your V max from the previous day's assignment. And typically that V max is usually around 0.3 meters per second. Okay? It isn't really, really fast, but it's typically around 0.3. So what we're going to do is that we're going to figure out what the velocity is as a function of time. Now, if you think this through, okay, if you think this through, as this thing is oscillating, okay, and before you even do any calculations, you should have a fairly good idea of what's going to take place. So remember, at time 0, we started with that mass at the top of the oscillation. So at time 0, what do you think my velocity should be? 0. Okay? Your position time graph had a slope of 0. So if this equation works, we should get the value of time of 0. So at 1/4 t, at 1/2, 3/4, 1 t. So if you think about what's going to happen, you should get an idea of, oh, when is it going to have that maximum velocity? You can go and you can look at your graph. You can look at your velocity time graph and go, oh, okay, great. When is that maximum velocity taking place? Now, you can look at this as mathematically. Now, I tell you specifically, I want you to use the Vmax as 0.3, okay? You've calculated it, and this is pretty close to what you should have gotten. But when you're doing this question, I specifically want you to use 0.3 meters per second as your Vmax. That way, when I grade it, I can use like a standard answer key and there isn't a bunch of variation. So, look at this in terms of this value of t. So at time equals 0, and by the way, make sure your calculator is in radian mode, okay? Make sure you're in radian mode. So if I plug in time 0, I'm taking the sine of 0. So what's the sine of 0?
0.
It's either 0 or it's 1. What's the sine of 0? Mr. Rogers?
1. 0.
0. Okay? So when little t equals 0, you're taking the sine of 0, which is 0. So guess what? Your velocity at time 0 is going to be
0.
0. Okay? Which is why your velocity time graph starts at
0.
0, which is why your position time graph has a tangent line slope of 0. Okay? Now, when you go to 1/2 t, excuse me, 1/4 t, okay? So there's a couple of ways you can do this depending upon your preference. If you like smash mouth physics, here's what you can do. To do that 1/4 t, let's say that the period for your oscillation was 1 second. Okay, so if you go to the front of the lab and your period of oscillation is 1 second. So if you want 1/4 t, that would be 0.25 seconds times 2 pi. So you could actually plug in these numbers. So if you like numbers, like Bergkamp, it flips me out when you do the variables thing. I don't like it, and some people do. They get flipped out. Come in here and put, even if your period wasn't exactly 1 second, make it a second, okay? Because it doesn't make any difference anyway. So let t be 1 second. Let this be 0.25 seconds. So look what happens, right? So you got 0.25 times 2 divided by 1. You don't have to worry about the 1, right? So you could come in here and plug into your calculator, and again, make sure that you are in radian mode. And you could plug in this 2 pi, sine of 2 pi times 0.25 multiplied by that negative V max of negative 0.3 meters per second, and you can calculate the velocity that way. So if you like smash mouth physics, put in 0.25 seconds. Let the period be 1 second, let that be 0.25. It's cool. Down here at 1/2 t, you would take 2 pi times 0.5 seconds. 3/4 t, you would be 0.75. T would just be 1. Okay? So if you like smash mouth physics, let t be 0.25, 0.5, whatever that time is, and let the whole period be 1 second of oscillation. It's cool. It works. Okay? Now, the other thing that you can do is a little bit more elegant. Again, it's a personal preference thing. So the other thing that you could do is go sine of 2 pi, and then you've got 1/4 t over t. The t's cancel out. So I have 1/4 times 2 pi, which is the same as taking the sine of pi over 2, right? Because 2 over 4 is 1/2. So if you know your trig functions, and if you know what the sine of pi over 2 is, it just saves you multiplexing numbers into a calculator. Some people like this, okay? Because they know their trig functions. If you don't know your trig functions and you only trust your calculator, there you go. Put in those numbers. So what you should see is that on this question, because of the specific values that I picked, your answers are only going to be 0 and then plus 0.3 or negative 0.3. That's the only answers that you should get through here. So take a second, do those calculations, because we've got to have those to do the next thing. So take a second, get those answers. Pay attention to the sign. So Kelsey, stop that camera for a second. Just press that silver button. Okay, so this is where, for those of you that have studied calculus or you look at the graphs, so here's what I'm looking for in number 3. So based upon your results from number 2, explain the correlation between the amplitude versus time graph and the velocity versus time graph. So look at this in terms of tangent lines, okay? So if you were to go through and look at your position time graph, like at time 0, and draw the slope of that tangent line, how would that correspond with this data that you just generated? So if you look at this, basically, without ruining the surprise, here's what you should have, is that this is going to be 0, and you can have negative 0.3 meters per second, and then you're going to go back to 0, and then it's going to be positive 0.3, okay? So it's going to oscillate back and forth. So here's the deal. So at time equals 0 on your position time graph, that started up here, and you would have a slope of a tangent line which is 0. That's why your velocity at time 0 is 0, because that's the slope of that tangent line. Now, when you get to 1/4 t, that tangent line is going to be like this. Notice that this is the steepest possible tangent line, is going to be right here in the middle. So this is when you have your maximum negative velocity, which is going to be your steepest slope. Now, once you get past that point, that tangent line is going to start to flatten out, and then it's going to go to 0. So when this position time graph has a relative maximum or a relative minimum, that's when your velocity is going to go to 0. So if you were to take the derivative, for those of you that have done calculus, if you take the derivative and evaluate it at those points, the derivative, remember, gives you the slope of your tangent lines. That's why those are going to have slopes of 0 at those points. Okay, so here's a little tie-in with the calculus. So, then I'm going to ask you this. What's the slope of the tangent lines of the amplitude at 1/2 t and t? So, you're going to come up here and go, oh, 1/2 t and t, all right? What's that slope? Then, explain that correlation. Why does it have that slope and explain this in terms of physically what is happening to the system, okay? It's like, oh, it's at the top of the oscillation, or is it the middle of the oscillation, or is it at the bottom of the oscillation? That's how you want to tackle explaining this. Now, this next equation, and there's going to be some variation on this. So, and by the way, these equations are not on your equation sheet. Do not memorize these. These, like this, A max equals negative Km over x. I will give you this equation, okay? Don't memorize it. If you need it on the test, I will give it to you. Now, here's the deal. So, K is going to be whatever your spring constant is, okay? This is going to be the mass, which is 1.5 kilograms, okay? Because that was the mass that we had oscillating. And we're going to let x be 0.05 meters. So in number 6, just so that we're all getting the same answer, we're going to let that be 0.05 meters. Okay? So, now, think this through. Right? I want you to think this through in terms of how this equation is physically going to play out. So, if I've got, we'll try and do this without it turning into a disaster again. Awkward. So, as I make this spring oscillate, right? Okay? So if you look at that oscillation in terms of this equation, so notice that this mass is in the denominator. So as mass gets bigger, what's going to happen to your maximum acceleration? What did you say, party girl?
It's going to decrease.
It's going to decrease. So when the mass becomes bigger and bigger and bigger, you get a smaller and smaller maximum acceleration. So if you look at just physically, when I put that 0.5 kilogram mass on there, it's like doink, 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 right? Okay, it goes pretty fast. Now, if I put 1.5 kilograms on there, we'll try and do this. Oh, could I do it? Could I do it? Maybe. Okay? So now, just watch what happens. Okay? So when I had just the 0.5 kilogram mass, it was like doink, 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 doink. Okay? That's that sound it was making on an atomic level. And it vibrated really quickly, right? Wow, big acceleration. Now, when I put more mass on here, okay, notice that it's like watching it in slow motion. So I don't get as big an acceleration because of the fact that I have more mass in the system, right? The more mass that you have, the more inertia that you have, the harder it is to get it to slow down, but the harder it is to get it to move. So this is where you want to be able to look at an equation and play the what-if game, okay? So, here's the deal. A equals negative K M, so you're gonna have your slope, okay? That's what's gonna be different for everybody. Your mass is gonna be 1.5 kilograms, and we're gonna let the amplitude be 0.05 meters. So you're gonna calculate that maximum negative acceleration, which is oddly enough gonna be either at the top or the bottom of that oscillation, because that's when you're gonna get your maximum net force, so that's when you're gonna get your maximum acceleration. So then, once you get this number, okay, then you're going to plug it into this equation. So this is going to get you your actual acceleration. Now, don't make this like a negative of a negative. This is just negative A max, okay? Don't make it like a negative of a negative. That would just get weird. So just take that maximum acceleration, cosine 2 pi t over t. And again, I don't care how you do this. You can plug in 0 and let the period be 1 second. You can plug in 0.25, you can plug in 0.5, 0.75. If you just want to look at it in terms of, oh, calculating out the t, and then figuring this as a fraction of 2 pi, I don't care, okay? It makes me no difference. But here's what you're going to, now you're going to use this equation to figure out these numbers. So let's just make sure everybody's cool with how you should start. So let me move this down. So that you all spring down. So that first acceleration, depending upon your spring constant, is going to be something around negative 2 meters per second squared. Okay? So that's about what that first acceleration is going to be. So go down, and this is why this is this negative value. This is why your acceleration time graph started down there at the bottom. So right quick, go through here, calculate this. Then on number 9, indicate if the net force is positive, negative, or 0. So guess what? At time 0, I'm going to have a negative acceleration. What's the sign of my net force?
Negative.
Negative. Don't make it difficult. Okay? So go ahead and do 8 and 9 right quick. And then if you want to get aggressive while the camera's still going, we'll just talk about all of this through 10 and 11, because then we're going to be done with the graphs. So I'm just going to go ahead and explain 10 and 11. So you go to the velocity time graph, indicate the sign of the acceleration in each segment. So you're going to go all the way back to your velocity time graph. You're going to tell me, is the acceleration positive or is the acceleration negative? Okay? And don't make tiny little marks that you think I'm going to see. If you want to like color code it, if you if you have Joel, if you want to bust out your colored pencils and make them look, oh, I'm going to make red be negative and blue be positive. If you just want to like draw like vertical asymptotes and go in this region is positive and this region is negative, if you want to put plus or minus signs on, I don't care. Just make sure that I know exactly what you're trying to indicate. So then, on number 11, and do not freehand what I want done on number 11. Take some type of straight edge, and you're going to draw the tangent lines at 1/4 t and 3/4 t on the velocity time graph. So you're going to go to the velocity time graph, and this is something new. We've never talked about or drawn tangent lines on velocity time graphs. This is what's going to happen here. So you're going to go only at 2 places, 1/4 t and 3/4 t, and you're going to draw tangent lines at those. Sloping, horizontal, whatever that's going to be. And then how does that correspond to the acceleration time graph? So I'm going to stop talking, go ahead and work through number 11. So, Kelsey, stop that camera again. Okay, so you've got enough information to get you through this. Now, when you get to question number 12, it says, how is gravitational mass different from inertial mass? When I give you a question like this, you want to use the word while in your answer, okay? So you could say, like, if I could say, what's the difference between Party Girl and Rachel, okay? So and you want to use the word while, so you can say, oh, Party Girl likes to party while Rachel is a little bit more chilled out, okay? So that's how you want to answer this. You have access to Google, you can ask your phone, you can look it up, whatever. But you want to use the word while in this answer. So you can say, gravitational mass is da-da-da-da, while inertial mass is da-da-da-da-da. Okay? I'm not asking you what's the definition of gravitational mass. I'm asking you, how is that different? So you need to figure out, okay, what's the difference between the two? So you want to use the word while, and you want to reference both of these. Okay, so you're going to say gravitational mass is da-da-da-da, while inertial mass is da-da-da-da. Okay? Use the word while and reference both answers on number 12. Now, when you get to number 13, okay? So, ultimate field trip, we go to the International Space Station. You're going to try and figure out the inertial mass of a block of iron. So, describe how you could determine the inertial mass of the block, assuming that you have a spring with a known spring constant. Be specific about what you would measure and the equations you would use. So, you want to look and say, okay, hey, here's a spring. All right, I've got a spring. Kind of like the deal that we made oscillate. Okay? So, when you answer this, look at what I'm asking for. I want you to tell me what equations that you're going to use. Are you going to use F equals ma? Are you going to use that equation? What are you going to use? Then, knowing that, what are you going to measure? And then how are you going to use that within this equation to solve for mass? So you're going to say, ultimately you would say, okay, hey, I'm going to measure the relative humidity inside the International Space Station and the number of inches of snow we're expected to get tonight. And then I'm going to plug that into this equation, and that's going to allow me to get mass. None of which is relevant to this calculation, but you get the point. Now, when you get to number 14, okay, let's just say, we get there, and we realize that we don't have the spring. It's like, well, okay? But you do have a force sensor, okay, like this, all right? You all have seen these, right? So we can turn this on. And so, like, let's say here's this mass, right? So we could hook this up, and we can measure, this is going to be important. The force sensor, oddly enough, measures, wait for it, force. Shocking, I know. So I can know how much force I applied to it. Since you all, with a little bit of prompting, realize that force equals mass times acceleration, we don't have to worry about an effective gravitational field because we're floating in the International Space Station. So we can measure force, right? Okay. We also have a meter stick. Oh, maybe we can measure length. And a stopwatch. Oh, maybe we can measure time. So notice that I've given you like 1, 2, 3, 4, 5 lines here. Okay? Means I want a decent explanation. So you're going to say, how are you going to use that force sensor? Let me give you a hint. You're going to use your force sensor to get an acceleration. Then, once you get your acceleration, how can you use the meter stick and the stopwatch to figure out the mass? Okay? So you're going to work off the idea that F equals ma. You can measure the force, right? But you can't directly measure acceleration. But if you know a distance and a time, then you can calculate the acceleration. Once you know the acceleration and you know the force, then you can solve for mass. So, let me give you a hint. Use the stopwatch and the meter stick in an equation to determine the acceleration. Know how much force that you apply, use that to calculate the mass. Okay? So, and notice, I tell you, and the equation you would use, again, I want to see the equation you would use to solve for that acceleration. Just like up here, I want to see the equation that you're going to use to determine the mass. Okay? So that's going to be part, you should have equations in this answer, and you should have equations in this answer, explanations, explanations, okay? This cannot be done in one line. This, and I'm not saying you have to use all 5 lines, but you just can't say, oh, F equals MA, and then da da da. You're going to explain how you're going to do this. Okay. Now, let's talk about this next part, and then I'm going to turn you loose. So, let me explain what's going to happen on question number 15. The whole key to question 15 is that we're going to oscillate a spring horizontally, okay? This isn't going to be a vertical oscillation. It's only going to be a horizontal oscillation. So, if I take this spring, okay? Okay? So, imagine I could take this spring, I could hook it up, and I'm going to stretch it out, and then I'm going to let this, I'm going to have a mass on the end of it that's going to oscillate back and forth on the end of this spring. Okay? I'm not going like this. There's no gravitational. It's only going like this. So, because it's oscillating horizontally, let's make sure everybody's cool with this answer. What's the only 2 types of energy I can have?
Potential and kinetic.
Potential and kinetic. I can have us, and I can have energy in the spring, and I can have translational kinetic energy. So this is going to be us and KT. So, then you get this, knowing the amplitude of the horizontal oscillation, what equation could be used to determine the total energy of the system and what value is assumed to be 0? So here's what I'm looking for on this one. So imagine this spring, we're watching this in slow motion and it's going like this, okay? Going back and forth like this. So if we can figure out at one point what all the energy is, then we know that has to be the total energy of the system. So, when this thing is completely stretched out like this, okay, and it stopped, what's the only type of energy it would have?
Us.
Us. Now, how do you calculate us?
1/2 kx².
So, now let me give you a hint. Us is 1/2 kx squared. Okay, it's a generic way to calculate us. But if you're talking about maximum us, okay, sounds odd. Like that could be a counseling service I could have. Come visit maximum us. I'll tell you how to, no, that would be horrible. That would be poor. So if you want the maximum us, guess what? That's going to be 1/2 k amplitude squared. Because remember, your amplitude is your maximum displacement from where it's at equilibrium. So your maximum potential energy of us is going to be 1/2 ka². So these 2 equations are the exact same. Okay? We're just, instead of a generic x, we're going to let it be the amplitude. Okay? Now, when x equals 0, okay? When x equals 0, and there's no amplitude at all, okay, there's no distortion at all, how much us do you have? 0. Guess what? That's when you're going to have maximum kinetic energy. Because it's going to, on one extreme, this amplitude is out like this. It stopped because it's going to change the direction. Oh, I don't have any kinetic energy. That's my amplitude. Oh, that's my maximum us. Now, when it pulls back and it goes through that equilibrium point, guess what? Oh, there's no us. Guess what? It's all kinetic energy at that point. Oh, right. Did we start that camera back up?
Yeah.
Okay, good. Couldn't remember. Because it kind of flipped out just a second. So, and guess what? That's when you're going to have maximum kinetic energy. So when you don't have any amplitude, you don't have any us, it's all kinetic. But when it's maximum us, you don't have any kinetic energy, because that's when you're going to stop to change direction. Okay? Now, let me explain the terminology on question number 18. Assuming that there is no friction, assuming that there is friction between the block, draw an energy time diagram from the mechanical energy of the block, assuming that it starts at its largest amplitude. Now, Notice with this one, I'm talking about your mechanical energy, which is like mechanical energy is a fancy word for saying kinetic energy, okay? So this is going to be important. I'm going to start this thing at maximum amplitude. So how much kinetic energy am I going to have at maximum amplitude? What's this going to start off at? Way up here or way down here? Party girl. Top or bottom?
Bottom.
Bottom. Because here's the deal. I want kinetic energy, but I'm going to start at its largest amplitude. So I'm going to start way out here, right? Have that visual. I'm going to start way out here. So I'm not going to have any kinetic energy. Okay? And mechanical means kinetic energy at this point. So this is going to start at 0. And then what's it going to do? So then this thing is going to start to move. So my energy is going to go up, right? And then it's going to drop back down. Now, but because there's friction, what's going to happen to that amount of energy in the system? What's it eventually going to go to? There's going to be friction. So it oscillates. What's it going to start to do?
Decrease.
Yeah, because you're going to generate thermal energy. So this is just going to go like this, and it's just going to get smaller and smaller and smaller and smaller and smaller because there's friction. If there was no friction, it would just keep going back and forth like this. Okay? Now, when you get to question number 19, now you hold on to that first answer that you gave me. Okay? On 19, I said, assuming that there is friction with the block, draw an energy time diagram for the system consisting of both the block and the spring. Okay? The block and the spring. So, because I'm talking about the sum of the potential energy and the kinetic energy, even when it's stretched out, that's when it's going to start at its maximum. Now, this is the sum of the two values. So this is going to start up here. So, since it's talking about the sum, what's this thing going to do? Is it going to go up? Is it going to go down? Down, because I'm going to lose energy to friction. I'm going to generate thermal energy. So this graph just starts here, and it's going to go down like this, because I'm losing energy to thermal. Okay? And again, if it was a perfectly frictionless system, this line would just go across like this, and there would be no variation at all. Now, look over onto this last page. Now, this question here has nothing to do with what we've already done. Okay? Not directly anyway. So, here's the deal. So this is going to be important. I got a 0.125 kilogram mass. I'm going to oscillate it, and this is the object's position and velocity. So here's position, here's the velocity, right? Now, so this is the position relative to the ground. So if you look at what's going to happen, so the ground is here. So this is my position time graph. So this thing would start at the bottom, then it's going to go up to 1 meter, and then it's going to come back down, go up to 1 meter, come back down. So notice on this system, the amplitude isn't changing, so I'm not losing any energy. So again, you can visualize this as this spring being pulled down, and there's a pencil attached to it, and this spring is going to go back and forth, and I'm going to drag this piece of paper along. And imagine that that pencil is making these curves as this line is going past. Now, this is the velocity time graph. So imagine down here I've got a sensor that's measuring the velocity of this. Now, notice this starts at 0, goes positive, goes negative, positive, negative, and it goes through 0. So this is like, this whole thing is like the culmination of this whole thing. Now, just so I want to, because this is going to be important later on, this is like 1.5, so we're going to call this maximum velocity here, so that everybody's using the same number. we're gonna call that, I screwed that whole thing up, hold on. So, everybody's using the same numbers. We're gonna call this maximum velocity here 1.6 meters per second, okay? You're gonna need that for some calculations later on. So this is gonna be 1.6 meters per second. Okay. So, you've got on 20, so, because I wanna make sure everybody's cool with this. This thing is oscillating like this. So now we're back to a vertical oscillation, okay? So at any given point, what three types of energy can I have? Rachel Meeker, what's one of them? I could have UG, because it's oscillating vertically. Tina, what else could I have?
Us.
I could have us. Kelsey, what's the third type of energy could I have?
Kinetic.
Kinetic. So I could have us, UG, kinetic. So those are the three types of energy that I could have. Now, this is mathematically going to get a little bit weird. So I'm just going to work through this so that everybody has this right, because if you haven't done trig functions lately, this gets weird. So basically, on this one, what we're saying is that the total amount of energy in the system is going to be the sum of the kinetic energy and the potential energy. So this U is either going to be us or it's going to be UG. So they just lumped it together in terms of U, okay? So, setting E total equal to the maximum kinetic energy, okay, this is where everything kind of comes together. So when you're in the middle of that oscillation, you're going to have your maximum velocity, okay? So you're going to have maximum kinetic energy because you're in the middle of the oscillation. So write an expression solving E total for U. So this isn't tough. All you have to do is go, oh, U is going to equal E total minus K, okay? Because it basically says, oh, solve this equation for U. So what this means is at any point, to calculate my potential energy, I take the total energy of the system and subtract how much of it is kinetic. Now, think this through, okay? Let's just say the total energy of the system is 2 joules. Okay, let's just say it's 2 joules, right? Let's just say. So if the total energy of the system is 2 joules, that's like me walking in and I have $2 in change, okay? I've got 8 quarters. So I could give Kelsey 50 cents, I could give Tina 50 cents, and I could give Party Girl $1, okay? Everything's going to add up to $2. Or I could say, hey, Kelsey, you're going down to I'm just going to give you all $2, okay? So I give all $2 to Kelsey, okay? But no matter what, everything's got to add up to 2. So think about this. If I don't have any potential energy, if this is 0, okay? If I have no potential energy, that means this, my total energy would be 2, means my kinetic energy would be 2. That's what's going to happen in the middle of the oscillation. Because I don't have any U, it's all going to be this. Or if I know that I don't have any kinetic energy at the top and the bottom, when I don't have any kinetic energy, that means my U is going to be the total energy at that point. Okay? Cool with this idea. Now, the equation, and this is an equation that you've seen before, can be used to determine the velocity at any point. Taking that equation for kinetic energy, insert this into the function for the velocity. So this is where this gets a little bit weird. So I'm just going to rewrite this. I got to write this bigger because so that you all can see it. That's max squared. Okay. So let me explain the ugliness of this trig function equation. So all this is saying is that at any given point, you could have all kinetic energy or you could have all potential energy. So all I did here is said, okay, if it's all kinetic energy, that's going to be 1/2 mv max squared. So this is just kinetic energy, 1/2 mv squared. But I specifically put it in terms of v max. Now, all I did here was that I said, okay, that's going to equal 1/2 m, and then I took this right here, v max sine 2 pi t over t, and I squared that and put that in here for the velocity. Okay? So your v max is going to be a fixed value. This is going to be this 1.6 meters per second. So what this is getting you here is what's the velocity at certain points. So obviously if this is 0, if this part is 0, that means your maximum u is going to be all kinetic. Okay? Now if this mathematically works out to be the same value as this, then there is no u, okay, because there's no energy stored. So all I did here, and this is the one that you really need to answer question number 24. So just so you can read this, this is 1/2 m v max squared, and you're going to go up to the graph. This is going to be this 1.6 meters per second. You don't have to calculate it. You can look at the graph. This is 1.6 meters per second. The mass is 0.125 kilograms. Okay? Now, this is 1 minus sine squared 2 pi little t over big T, and then close the bracket. So all I did was I took this and I factored out 1/2 mv max squared. Okay, that's all I did. Okay, so I took this and factored this out. So this is the heart and soul of what you're going to need to do this. So what you're going to do is that you're going to take the 0.125, the V max squared, get this number. Then you're going to go to here and you're going to plug in 0, 0.25 seconds, 0.5 seconds, 0.75 seconds, and 1 second. And then you're going to calculate that value of u at those points. Okay? Make sure that you are in radian mode. Then that should allow you then to answer the questions on the back and draw the graphs. Now, let me give you a hint about what you should get for question number 27. Your answer to number 27, that K value should be around 5 newtons per meter. Okay? So, and with this one, you're going to go T equals 2 pi square root of m over K. So, you're going to start with this equation, and then you're going to solve for the spring constant K. So, that should be around 5. Your answer to 29 should be around 10. So here's what's going to happen tomorrow. I'm going to dump out a short video that kind of finishes this up. If you want to look over those multiple choice questions, if you have anything you want me to go over in the multiple choice, but the video tomorrow is going to be pretty short. I'm just going to go through and summarize all of this. Okay, this is due on Thursday. Okay? All right, be free.
What is that? The square root of what over K?
M over K.